So welcome to a new week. So the topic this week is something which most of you have seen before. So we're going to remind you a little bit about forces, Newton's law, motion examples, and topics which will again be related to the exercises which we're going to solve. And we're also going to look at how to actually compute things, how to set up a program. We're also going to remind you a little bit about the scientific method itself. So I just wanted to, in the very beginning, to give you some quick messages. For those of you online, there is a link to the website where you find basically all the material. The basic website, there is a small addition here now. So if you scroll down and look at, for instance, the previous week, what we have done, in addition to upload the video of the lecture, we also brought in subtitles. So I obviously do have an accent, and in many cases, it's actually okay to have the subtitles. Now, the thing which we are going to do during the lectures is that we will upload the video immediately. So that's going to be like a raw dump of the lecture itself. And for those of you who are impatient, you can always look back at that one. There won't be subtitles because the automatic generation of subtitles, when you upload it to YouTube, it takes something like, depending on the length of the video, it takes something like 5 to 10 hours. So typically what you will find, if you look at the summary from last week here, you will find the video without subtitles, and then there's one with subtitles. The subtitles which you get from YouTube are actually pretty good. They are much better than the transcript which you see here on the screen. So that's a kind of service, and it's always nice to look at the subtitles. In case there were words which are unclear, we try to edit the subtitles as well in order to avoid typos and misconceptions. But please let us know if if you spot errors in the subtitles and so on. Okay, so this is where you find basically the weekly schedule and the teaching plan and what we have done. Now, if we go back to the topics this week, what we want to do now is actually to revisit Newton's laws, and we are going to look at perhaps a not too exciting problem. That's of a falling object, and that's going to be the topic. Yes. Yeah. Does it sound okay with the, or is it not functioning? So this is not functioning, eh? Let me just try to switch it off. We'll try again. Is that better? No, I think, what about now? Does it work better? So I'm going to try to, for those of you online, we have a small audio problem here. So I'm going to try the other one and see if that works a little bit better. Well, let's try that one. So they made some changes. Is this better? Okay, excellent. So the topic this week is about Newton's laws and how to apply them for specific problems. We are going to look at the problem which we started to develop last week of a falling object. And then we are going to look at how we can actually implement this numerically, because that's going to be a topic for next week, one of the exercises, the numerical exercise. We are going to look at a falling object in 2 dimensions, where we have an air resistance term which comes in and changes this plane acceleration of gravity, which is just a constant then. You will always find this kind of link to material, which we normally advise you to take a look at before you come to the lectures. So you can, if you scroll down here, you can see the kind of topics which we will try to cover and where you will find relevant reading material. So before we move on now, I wanted to quickly remind you of what we did last week and where we ended, and the kind of equations which we are going to work a little bit with as an example. On Friday, we are going to have again a kind of flip situation where we will discuss some examples. You will also find videos of examples which we have elaborated and which you can look at. And in case they mimic the exercises, you may find inspiration or hints and guidance for solving the exercises, the weekly exercises. Then we're going to use the rest of Friday to look at the next homework set. If you're not yet done with the present one, which is due on Friday in the evening, you can keep working on that one as well. So we typically make public the weekly exercises roughly 10 days, 2 weeks before the deadline. So that means that we will always have a kind of mix of people solving the next set and those solving the previous set. Okay, so let's switch to the whiteboard here and look at where we were last week. Just bring that up. So last week, the case we started with was we simply stated that we had a falling object. There is no air resistance, no nothing. It's simply an object in a gravitational field. And the assumption we made then, without deriving an equation, we simply stated then that the position as a function of time, y of t, so this is an object falling down, just in one direction. It's a one-dimensional problem. This y of t was given by an initial position y0 minus 1/2 times g times time squared. And what we did last week was actually to derive this equation. And what we did then was simply to integrate up. We got the velocity, starting with an expression for the acceleration. We got the velocity, and then we integrated up the velocity again, and then we got the final position. But we started from that case. And let me quickly remind you of some of the notation which we're going to use. So when we write this y0, this is normally the position or the variable y at the time t0. So this is just a shorthand which we are using. So you can then say that the initial time is something we will always label with t0. Then what we are going to do is that we are going to discretize. So if you look at the exercise which we have for this week, where you're looking at Usain Bolt's run for the 100-meter, what we have then is measurements of position as functions of time. So these are discrete times. That means that we are going to have a final time, and we are going to label that with a tn here instead of a t final. So time is a variable which now lives between t0 and t of n. Now, since we will always deal with some discrete variables, what we will have then is a t is actually equal to a set of variables from t0, t1, t2, and all the way up to tn minus 1 and up to t of n. So these are the actual values of t. And what we are going to assume in most of the cases we have is that time is a variable which is equally spaced. So we are going to say now that the t of I, which is a time at a given time ti, this is now given by t0 plus I times a variable delta t, which we are going to call the time step. And I goes from 0, 1, 2, up to n here. Now, when you're doing this numerically, like you did in the first exercise set, exercise 6, we're just punching in the data which you have from a measurement. Then you're setting up an array or a vector of entries for time and entries for the position. So what we end up with then is we can predefine this delta t. That's one possibility. And that means that we would find an array of t. So array of t values, which then is something we could set up with NumPy. If you're using, since we're going to use Python, we'll call a NumPy with that. And there's a function which is called arange. And we would typically then set t0, tn, as a function of delta t. So that's going to find out how many values you're going to have when you have predefined delta t. So that's one possible way. Another possible way is actually that you now say that t, or delta t, so define the number of points, define n, the number of points we have, and then we would simply set delta t is now given by the final t minus the initial t divided by the number of points. So that's another way of setting it up, but then you have to fill in an array for time. So that means that you would then have to have a loop where you define for I equals 0 up to n, and then you would simply have t of I, which is equal to this time t0 you have defined. So let's just write it like that, plus I times a delta t, which you have defined. So I'm not writing an explicit Python code. I'm just setting this up as a kind of pseudo algorithm here for you. So this is the way you would then start setting it up yourself if you have defined just a number of integration points. So what we did last time was actually to integrate up. So let me just quickly remind you. So we started with Newton's law. And when we had Newton's law in this specific case, we had a force which now depends on a constant actually. So we have a force which is given by time. It's actually a time independent force. And we simply had this as a minus g multiplied with the mass of the object. So that means that our acceleration is now just given by a constant. And what we did last time then was to integrate up. So we would now take Newton's law, because this acceleration m times a, which in our case is equal to minus n times g, that is actually equal to mass times the derivative of velocity with respect to time, which we again can rewrite as m times the second derivative of y with respect to time here. So these are the equations which we used last time to integrate up. Now, the standard way you would use to solve these equations, if you can do it analytically, you would just simply integrate up. But the same recipe, which you are going to call approach number 2, is a numerical approach where we actually are going to use something like Euler's method or modification of Euler's method to integrate up the equations. So when you have a second order differential equation, which is the equation you see here, this is a second order differential equation. What we would typically do then is to split that in two first order differential equations. So it means that if we now divide by n, so we would simply have a is equal to the second derivative with respect to position of dt. And what you would do next is simply to rewrite this, because then you would have that a is actually equal to the velocity. And now this velocity is a scalar because we are just in one dimension. We don't need to think of vectors. And a new equation which says that the velocity is actually the derivative of dy dt. These are actually the equation which we solved last time when we integrated. So when we integrated then, what we did, if we take this equation here, so in our case, there's something I also want to remark to you all, is that in basically all the calculations we are going to do now, this quantity is known. Velocity is normally not known. So this is an unknown quantity. The same applies to y, and the same to the velocity which we have here. Now, time is something we have defined because we have a different time, we have a specific time interval, and that gives us time from an initial time to a final time. So when we are going to analyze a physical problem, we will always know the acceleration. That is the most common case. So when you know the acceleration, when you have analyzed the problem, you have sorted out the forces, then you have an expression normally for the acceleration. And when you have the acceleration, yeah. Yes, go ahead, please.
Saying about V and Y?
So
it means they're not unknown.
They are unknown. Oh, sorry. This is, guys, I actually, it should be unknown.
Okay.
Sorry, this is me. I was actually planning to write not known, and instead I write not unknown. So it's actually unknown. Sorry for this. Thanks for noting that one. This was a lapsus from my side. So what we did last time, we simply took this equation which you have here, the equation for the acceleration, and we multiplied with the dt on both sides. So we got an equation which went like this. So we have a times dt. This depends only on time on this side, and then we have dv. And then we integrated up. So then we integrated from a time t0, and then we can take a time tn, and we have a times dt. So this equation depends only on time because we have dt. And then we took the other equation here, and then we integrated up from a v0, an initial velocity, which is known. So we have, so the other known quantity are the initial velocities and the initial positions. That's the way we specify the problem. So I'm repeating some of these things because when you're setting up a problem to solve, you have to define the initial conditions. Because if you don't define initial conditions, you won't be able to find the solutions because you will have an infinity of solutions. And we are looking at a specific solution, which is just governed by the initial conditions. So these are things, yeah, go ahead.
What's that variable attached to the t at the top of the integral? Is that the v?
So at the top of the integral, so this is v0, and this will be the final vn, and then we have dv here.
Or that's an n.
Yeah.
Okay.
So this is a tn, the final time. But what we can do now is simply let this. So when we integrate up here, what we would have, since the acceleration in this case is just minus g, so just a constant. What we got then when we integrated up is minus g, and then we had tn minus t0, and then on the right hand side we are just going to have vn minus v0. Then the standard choice is actually to let t0 be equal to 0. In this case, just for simplicity, we can also make v0 equal to 0. And then we let tn become a general time. We don't need to have the final time. So we just relabel it and just let it be t. So that means that we would have a vn, which goes over to v as a function of t, and that's simply equal to minus g times t. So this is the kind of recipe you would use if you can integrate analytically and you can find an analytical solution. Now, the next thing we did then was to integrate up and find the velocity. So we took the next equation, which was v equal to dy and dt. So we would multiply with dt on both sides and just repeat the same trick again. And when we did that, what we found, and this is where we basically ended last week, we ended up with a y0 minus 1/2 of g of t squared. Now, this is a pretty simple case. In the third homework set, you're going to get an example which you cannot integrate analytically. You actually have to solve it numerically. We are going to add an air resistance, and that air resistance is going to be proportional with the velocity. And then we can't integrate it. We won't find an analytical equation in 2 dimensions. So we are going to look in the homework set for next week, homework set 3, we are going to look at an object which falls in 2 dimensions. And in that specific case, we won't be able to perform this kind of operation analytically. And then we have to do it numerically. So last week, we announced this as approach number 2 here. So let's call that approach 2. So it's essentially, this means a numerical calculation. Now, if we go back to the basic equations, so we have separated out velocity and time and acceleration, which is equal to the derivative of the velocity. So these are 2 first-order differential equations. And what we do then when we are solving this numerically is that we are going to use numerical methods. And one of the standard methods is actually based on Taylor expansions. To demystify things, you will actually be surprised to see how many of the numerical methods are based on simple mathematics. So most of the methods which you use for solving equations numerically are based on manipulations of Taylor expansions. So in the beginning, people are a little bit skeptic. Is it that simple? So my answer to you guys, it's actually that simple. So let's look at the Taylor expansion and bring up the way we could solve these equations numerically, okay? Because that's something you will need in homework assignment number 3. Not this week, but next week. So let's take a brief excursion into Taylor expansion. That's the basic mathematical expression which we need, or mathematical tool which we need. Now let's put that up. So what we are going to need then, if we take y as an example, and this applies also to the velocity. So I'm going to put, you can put this into a parenthesis here. You can do exactly the same with velocity. And we are now just going to move 1 time step ahead. So we know that this is just given by y of t plus a y derivative evaluated at t. So derivative of y multiplied with delta t. And then we have a higher order term, which is proportional to the second derivative. And then we have y second derivative. And then we have the higher derivatives. So this is proportional with this time step cubed. Now, the simplest method we have is Euler's method. And that simply assumes that we can make delta t pretty small, and we can neglect terms which go like delta t squared or higher terms. So what we do then is to use Euler's method, which means that we are going to skip terms with delta t to powers of 2 and higher. And many of you who have taken CMSE 201, you've probably seen Euler's method. So Euler's method is like this kind of plain working horse in many solutions of differential equations. Later on, we will see that we can actually change it by some simple mathematical operations. And we are going to see that a little bit later. But Euler's method does a job in the beginning. So it's a simple to implement. So what we have, when we now look at the equation, we are going also to rewrite this delta t plus delta t. We're going to rewrite that in terms of a ti, a given time, plus delta t. And we are going to use a shorthand here with I plus 1. So we just move 1 time step ahead. That means that our right-hand side of that equation becomes y of I plus, and now we're going to put an equality sign here. So this is delta t times the derivative at the time t of I. So this is a kind of compact notation which lends itself to an easy implementation when you write your first code. So these will just be arrays which you have to fill in your program. That means when we look at this now, we know that y of I, the derivative is actually dy. So we have an expression for that. evaluated at t of I. And this is a velocity, v of I. So it means that the equation which we are going to have now, the approximation we have, is going to be equal to y of I plus delta t times v of I. Now I can do the same with the velocity. So my velocity, so I actually need to solve these two equations simultaneously. So I'm going to have a v of I plus a delta t. Now what's the derivative of the velocity? Anyone who sees that immediately? If you just go up a little bit, so we can actually plug that in. If you look at the equations we have here. Yeah, acceleration, exactly. So the derivative of the velocity is the acceleration calculated at this specific time, a of I. Now, if we now ring in things, what we know, the things which are marked in red now, so this is known, this is known, this is known, we have defined delta t, and then you see that the velocities and the positions are not known. What's also known is actually v0 and y0 are known. So on Friday, we are going to look at an example how we're going to solve this. So any questions so far? Is this okay? It's just too simple, or have you seen this before? Probably you've seen it in CMSE 201. But so we are going to have basically two approaches. So one, if we can integrate and can find an analytical solution, we would obviously use that and do it. If we cannot, then clearly we would have to resort to numerical integration. And this is essentially what we are doing here now. And you will see many examples of these. And the kind of code you will develop depends or relies on us finding the acceleration. So basically, all of classical mechanics is you analyzing the problem and finding the forces at play. And when you found the forces, you actually have the acceleration. When you have the acceleration, you can find the equations or the positions and the velocities. You can find the equations, or you can find a numerical solution. So mechanics is about the dynamics of moving objects under classical forces, where you have no quantum mechanics or relativistic effects. That's the standard classical mechanics, which we are going to deal with. So that means that we actually, there's a big question which I want us to think a little bit about now, because you see we have these quantities which are known. So we obviously define this one. We have found the velocity from the forces, and clearly we would also define the initial conditions. So you have a ball which is falling from a given height, and it has a given velocity. And now it's when we have to start thinking. So the thinking we need to do now is to start asking the questions, how do we find the forces? Or the forces, or the forces, or the force at play. So what we need to do now is to set up the basic stages in what we might call the scientific method, which is going to lead us to find the relevant forces. So what I'm going to do now is just to switch a little bit back to the slides. So let's just move back a little bit. Feel free to ask questions, by the way. So if things are unclear, just let me know. So the first thing, so what follows here is actually a little bit text. So the thing you have to ask yourself now, the first stage in what we will call the scientific method here is to identify our system. So what kind of object is moving? This is one of the first things we're going to ask ourselves. If you're studying the solar system, the objects which are going to move are the planets. The sun is much more massive, and we could then think of the sun being at rest roughly. And then we let the planets move around the sun. Then we need to think of what kind of data we have. So in the first homework, you actually have Usain Bolt moving. So you have position and time. That's the data you have. You may ask, how do you measure position? How do you measure velocity, acceleration? So I mentioned last week that one of the experiments you guys could actually do is to take your cell phones, because the cell phone has an accelerometer, and then you could take an elevator and you could measure your acceleration as a function of time. Then you would integrate it up, you would find the velocity, integrate another time, and then you find the height of the building. That's actually a way you could test whether your accelerometer is correct, because most likely you know the height of the building. That's a pretty neat example. You have to fix the initial conditions, and you have to sort out other aspects which you think are relevant for the system. So the first stage is actually you identifying the system. The next is you have to think of a model. So in the example we will see on Friday of a falling object, we are going to make a model for the air resistance. Now, friction itself, and you may be surprised to hear about that, there is no fundamental law in nature which gives you friction. So friction is something you would deduce from experiment, and you would often make an empirical formula for it. So that means that, like in one of the problems we are going to look at, you will see us assuming that friction is given by a constant times the velocity squared. This is something which is a good model if the object is moving at a high speed. If it moves at a low speed, what experiment shows is that the velocity of the resistance is proportional with just the velocity. We are coming back to that a little bit. You have to find the forces for the model. You have to identify the equation which govern the system. In our case, this is Newton's second law. That's the equation of motion. And then you have to find other elements which may define your model. The next stage is to solve the equations. And that's what we sketched now on the whiteboard. So when you have set up the problem, you have identified the objects which are moving, then we are going to implement Newton's second law. And we need to define initial conditions, typically the velocity and the position, and other conditions and boundary conditions. We will essentially never deal with boundary conditions, because that will lead us to partial differential equations, which many of you have not seen in mathematics courses yet. And then, when we all have solved the problem, you're happy, that's when you have to start thinking. So the thing we want to have you to develop is actually the tools to analyze the physics of a problem. And when you've analyzed the physics of the problem, that's when you have to start thinking. What does it mean? What do these specific results mean? Are these results which we expect, or is it just garbage? So it's a way, by solving this type of problems, it's a way for you to develop your intuition about a scientific problem. And that's the kind of thing we want you guys to develop during the semester. So the analyzation stage is equally important. So you would typically say, are these results reasonable? So if you run the solar system program, and for instance, the Earth doesn't move in a stable orbit, you know that that is not in accordance with observations. And then you may go back to your solver and say that I may have done something wrong here. You have to evaluate the answers and the implications, compare with experimental data. If you're solving the solar system, we know that the solar system from observation is stable. So if your code or your analysis says that the solar system is not stable, then we may have done something wrong. And all these steps which you see here, this kind of analysis stage feeds back to the first stage. So it may happen that the data were not good enough. You may have to collect more data. When you run things numerically, what would happen, if you look at this parameter delta t, which we put up, it may happen that that parameter is not fine enough. So you would have to make it smaller in order to get a stable solution. So that happens. Experimentally, that means that you may have to collect more data. So all these steps are actually the essential elements in the scientific inquiry. So when we are going to solve problems here, we are going to do it, if we can, by paper and pencil. You will see many classical paper and pencil exercises. But we're also going to solve problems which cannot be solved analytically by numerical computations. What you are going to see also is that the program you will write for the next assignment is a program you're going to reuse again and again and again. So you could just say you could have one program to rule all exercises. So for those of you who've seen the series of Lord of the Rings, this is just me rewriting about the ring, one ring to rule them all. You have one program to rule them all. Okay, so let's go back to the whiteboard a little bit and look at how we will analyze problems here. So one of the things we are going to look at now is a typical example where we are going to distinguish between the type of forces we will study in this course. So in this course, we are going to look at long-range forces and contact forces. These are the basic forces that play here. So let's take a look at the way we are going to analyze the system and find the final forces which are at play. So let's switch back to the whiteboard here. I'm just going to go back to the whiteboard. So if we now take a closer look at a typical problem, so we want to analyze a specific problem here. This is the analysis stage. So the first step actually is to divide the system into, so the first stage is divide system into an environment or into system, divide. Let me just take that one out. Divide into the specific system, into system and environment. And environment. So all forces which we are looking at now, they act, we have to identify all the forces which act on the system. And these forces are identifiable and they can be traced back to a cause from the environment. We are going to look at masses of the system which are additive. So if we have 10 objects, the total mass will be the mass of all the 10 objects. We are going to assume that these are so-called inertial masses, which means that the masses are determined by measuring the acceleration for a given applied force. We're assuming that in most cases that the masses are tiny, so they won't change. These are assumptions which we are making about the system. So the first thing is actually to divide into system and environment. So the forces which we are going to look at, so they are either, forces are either long range, or contact forces. These are the typical forces which we encounter when we deal with classical mechanics. Do you have an example of a long-range force, a force which acts on immense distances? Yeah. Gravity. So gravity. Gravity is one of these examples. So that's an example of a long-range force. There's another thing we won't consider in this course here. We have only external forces. So what does that mean? Now, it means that when we are looking at the system, we are not going to look at what we call internal forces. So if you look at an atom, you could think of the internal forces between the electrons in an atom. We are not going to look at those. We will think of an atom as one body. That means that there are no specific internal forces inside the atom which come at play in classical mechanics. So we will mainly just deal with external forces. These are the forces that play in this course. That means also that we won't consider the internal forces. The next thing we will do then is actually to draw a figure of the system. So we would find the object. So let's make an example here. Suppose we have a table here, and then we have a ball which is sliding on rolling on a table. So this ball, if we now want to dissect the problem, what we would have is a force from the table. So we're going to call this one N, and I'm going to put arrows just to indicate that this may not be a one-dimensional problem only. So this is normally what we call the force from the, or the normal force from the table. From the table. What we could have, in addition to that, would be some resistance or some friction. So we're just going to call this the friction from the table. It could be air resistance as well. So we just call this a friction term. It's now unspecified. Then there may be some effects due to different pressure. So this could be a buoyancy force. So this would be an FB here. So this would be something like, it could be due to a different air pressure, just an example of forces. And often what we will end up doing is to neglect some of these because we often tend to simplify. So it could be due to different air pressure. And then there is actually here in this figure here, I may have forgotten something. So I have the force from the table. There is some friction, which I haven't specified. There may be some forces due to different air. Yeah, there's something missing here, right? Yeah, gravity, right? So if you look at this problem here, the final one, which we haven't put up here, would be gravity. So let's call this just for G. And this is the gravitational force. So it's the gravitational force, as we said, this is a long-range force. So this is an example of a long-range force. So if you look at the other ones, which one of these would be a clear example of what you might call a contact force? Yeah. The normal force, yeah, exactly. And you could also think of friction as a typical contact force because that would deal with the way the elements interact with each other. And that is typically due to the contact. So that's also contact force. So you could say that the other forces are forces which we could think of as contact forces. Now, when you now have analyzed the problem here, then you would have the net force of the problem. So that means that what we would have then would be something like this. So we would have a net external force. And we would simply write this as an F net. This gives us now, if this is the mass of the object, it gives us the total acceleration. So the total acceleration is actually going to be the sum of all the acceleration from the different forces which are at play. So that would give us now G times this FB plus N times this F of D. Now I should put an arrow here. So when I put arrows, this is my way to indicate that these are vectors. And in my lecture notes, you will find them as bold-faced quantities. So, but on the whiteboard here, I use arrows to indicate that these are vectors. Now, in general, what you would have is that we could rewrite this in terms of, in general, this F net, this is the final force, could be the sum of all the different forces at play. So we could have something like this here. So sum over F of I, where these are the specific individual forces without us having specified them properly. Now, we are not yet done here. So we made a drawing. So typically what we make then is that we make a kind of closed graph where we isolate the object. And now we need to, when we do this, we obviously need to name all forces. And in one of the exercises for this week, you will actually see a case where you have to name the forces. And you can make the assumption that there is no air resistance. You can make assumption that there is, but you have to make a similar drawing and then analyze the problem and figure out which are the forces. So as I said last time, I hope you don't get offended if we do some repetition of what you've seen before, right? Because we're assuming that you've seen this back in Physics 181, most of you. So you would identify, name all forces. You would identify long-range forces and short-range forces. Long range and contact or short range, we often call them short range or just contact forces or short range. So like as we did in this drawing here. Then there is another problem, another thing here, which also is pretty important when you want to solve the problem. So if you look at the image or the different steps we did here, is there something which you think is missing? Something you would add if you want to solve the problem here? So what strikes you as one obvious thing to decide upon when you want to solve the problem? Let's see, yeah? Yeah, so what kind of word would you use for that?
The gravitational effect on the ball. So like,
yeah.
Ball like Mars or ball on Earth.
So would you think of something like a coordinate system? Would that say something?
Yeah.
So the what you said, I mean, is something you can translate into a specific system which you want to use to solve the problem. And sometimes you can find the solution easily if you run everything in a Cartesian system, or you can find it easier, you can find an easier solution if you transform to spherical coordinates. That depends on the type of forces at play. So the thing you need to decide upon then is actually the system or the coordinate system. Decide upon coordinate system. Now, all these elements here are actually spelled out in the lecture slides. So the forces are actually also additive, and the masses are additive. So the final net force is actually given by the sum of all these forces. And that gives us the acceleration. So that means that when you have done this exercise and you found the forces, you have the acceleration. Then you can actually go back and solve the equations. So what you would do then, when you have the forces here, you analyze the problem, you will go back here and you see that you have a acceleration here. When you found the forces, you have the acceleration. And then you can start solving the problem. So you having written a program like this, or having the possibility to solve it analytically, means that you can go back to this code or refinements of that, as you will see throughout the semester. Throughout the semester, we're actually going to repeat again and again these basic equations, which you see spelled out here, with some simple modifications. So these equations here just anticipate what you're going to see. If you have a force which depends only on position, that conserves energy. Euler's method does not conserve energy, and that's a serious drawback with the method. But we can actually make simple changes to that Taylor expansion and get an equation which actually solves or conserves energy and other physical quantities. So these are things to come, but the basic mathematics, if you've gotten the message which you have here, the basic mathematics and the basic numerical approaches we're going to use in this course, actually those which you see here. So this is a kind of way to look at classical mechanics from an overarching point of view. So I see the time is over. We also have office hours from now till roughly 5 o'clock. For those of you who want to hang around, either online, or if you have questions here, you can just hang around and ask. Else, we have the standard office hours. Lectures are being recorded, saved, and the video will be uploaded, and you will find this video online, and you can always revisit everything we've done here. And never, never hesitate to ask questions, please. Okay, see you all on Friday. Okay?
Okay, can I share my screen?
Yeah, absolutely. But I'm just going to stop.
Okay.